3, 2, 1. Okay, in this video I want to talk about integration by substitution. Integration by substitution uses all the same rules for integration that we've already learned, along with some of our derivative rules, and it's used for composite functions. So a composite function is basically something of the form like this: f of g of x. If you need to review composite functions, you might want to look back in the algebra section for the video on composite functions and just do a quick review of that. But the idea here is we'll have a situation where we have a composite function, and then the inside part of the composite function, the g of x, the derivative of that will also exist in the problem. All right, up to a constant multiple, but we'll talk about that. And then we make a substitution. U equals g of x. We take the derivative of u using the differential notation. We take the derivative of u, we substitute all that back into the problem, and then we'll have something that we can anti-differentiate. Alright, so before I get too deeply down a rabbit hole, let's look at an example of how this is going to work. So I have a situation here where if I wanted to, I could multiply out this part of the function here 5 times and just have a straightforward polynomial to anti-differentiate, but I'd rather not do that. And if I look, I've got right here x squared plus 1, and I've got right here 2x, which is the derivative of x squared plus 1. Alright, so I can make a substitution by letting u equal x squared plus 1, like that. And now I take the derivative of u, and again I'm going to use the differential notation because we are doing antiderivatives here. Alright, so the derivative of x squared is 2x, of 1 is 0, and then dx, again, because differential notation. Alright, so this now becomes, right, this is my u, and this, I can turn this around here. Let's turn this around here. X squared plus 1 to the 5th, so this is my u, and then I have 2x dx, and this is my du, according to what I just did over here. Alright, so this becomes now the antiderivative of u to the 5th du. And that I know how to take the antiderivative of, right? That is 1/6 u to the 6th plus c, which when I substitute back for u becomes 1/6 x squared plus 1 to the 6th plus c. Alright, so I was able to take what would have been a chore to multiply out and turn into a simple polynomial into just a couple of steps with a substitution and something that was easy to integrate. Alright, now sometimes this is referred to as the general power rule. I don't particularly like that notation, but it is the one that our textbook uses. Because the substitution method is a general method, okay, and it can be used on things other than the power rule. All right, let's look at some more examples here. All right, so I have another similar type of situation, but in this case, again, I have a composite function. So here is the inside of my composite function, the part that I want to make the u. This time it's being raised to the 2/3, so this time there is literally nothing I can do with this. I can't multiply it out 2/3, you know, by itself 2/3 times. But I can work the problem with a u substitution. Alright, I do have x to the 3rd plus 1 in here. The derivative of that is 3x squared, but I have the x squared. That's the important part. So if I come over here and do my u substitution, x to the 3rd plus 1, and I take the derivative, which would be 3x squared dx. Well, I'm really close, right? Because what do I have here? I've got the antiderivative. I've got my u part, right? The x to the third plus 1 to the 2/3. So I've got my u. And then I've got x squared dx. And that's not quite what I have for du, right? I'd like to have x squared dx for du, but I can get it. I can get that pretty easily just by dividing that 3 out. And I can do that as long as it's just a constant. So 1/3 du is going to be x squared dx. And then I can come over here and say this is 1/3 du. And because this is just a constant and this is all multiplication, I can pull the constant outside when I do the substitution. So that becomes 1/3 the antiderivative of u to the 2/3 du. And now I can take the antiderivative of that. Right, so the 1/3 just carries along. And then what do I do here? I have to add 1 to this. That becomes 5/3. So that is 3/5 u to the 5/3 plus c. Alright, and then I can clean up my fractions here. That's now 1/5. U is x to the third plus 1 to the 5/3 plus c. Alright, so you may have a situation where you don't have exactly du, but you're off by a factor of a constant. Alright, it has to be a constant for this to work right. Okay. And then if you have that, if that's what you got, you just divide the constant out of both sides, and then you have exactly what you need left in the problem. Alright, let's look at some other examples. Alright, how about here? This isn't a power rule, but it is still a composite function. Right? When you have a rational expression like this, again, 9 times out of 10, it's the denominator that is what you would consider the inside part of the composite function. Alright, so let's see what happens. If I take u to be the denominator, 3x squared plus 1, then du, the derivative of u, is going to be 6x dx. And notice what I have left here. I have x dx. Alright, that's what's left in the problem. So if I simply pull this 6 over to the other side, alright, I have u in the denominator, and I have 1/6 du in the numerator. Alright, so this becomes, again, 1/6 can come in front. So on top now I have x dx, which is du, over the denominator, which is u. Alright, and du over u, or 1 over u du, is exactly the form we need for the natural log. So that's ln of the absolute value of u plus c. So this becomes 1/6 ln the absolute value of 3x squared plus 1 plus c. In this case, you really don't need the absolute value markers because 3x squared plus 1 is always positive, but it's not wrong to put them in, so I'm going to leave them there. Alright, let's look at this one. Alright, I have another situation where I have a fraction. Alright, and remember I said 9 times out of 10 you're going to pick the whole denominator. Well, the difference here is that my denominator is itself a composite function. Alright, so I want to not take the whole denominator. I want to examine the problem and see which part I want to take. Alright, so if I just take x to the third minus 1, the derivative of x to the third is 3x squared, and that's what I have left on top. Alright, so that is going to be my choice for u. Alright, so du is going to be 3x squared dx. All right, and then I don't have the 3 up here, so that means I need to pull that over to the other side. All right, so now I have underneath the square root sign here, I have my u, and on top I have my 1/3 du. All right, so this becomes, again, the 1/3 can come outside, the antiderivative of du over the square root of u. All right, so I need to do a little more work here before I can take the antiderivative. All right, 1/3. The antiderivative now, the square root of u is u to the 1/2 in the denominator, so when I bring it up, u to the negative 1/2 du, and now I can just use a power rule on it. So this is again 1/3 times, add 1 to this and I get a positive 1/2, which means I get 2 over 1 times u to the 1/2 plus c. So this is going to be 2/3. And then what is u? U is x to the 3rd minus 1 to the 1/2 plus c. All right, that's good enough, but if you want to go the one extra step, right, 1/2 power is a square root, so that would be the square root of x to the 3rd minus 1 plus c, like that. All right. Okay, let's take a look at another one before I sum everything up. All right. Let's get a little more complicated here. I have a fraction. All right, so up until now I've been saying 9 out of 10 times you're going to take the denominator of the fraction. Well, this is like the last problem, one of those 1 out of 10 times when you're not going to do that. If I take the denominator to be my u, let's look at what happens. All right, if I do this, then my du is 2x dx. And nowhere else in the problem do I have a 2x dx. So that is the wrong way to go. All right, what else can I do? Well, if it's not going to be the denominator, maybe it's the numerator. All right, the numerator is e to the 1/2 x. Now that's fairly complicated. All right, I'd like to try and simplify what I choose a little bit more. So instead of taking e to the 1/2 to the 1 over x, I'm just going to take the 1 over x, and let's see what happens. All right, if I let u be 1 over x, then du is what? Well, let's work on this a little bit. This is x to the minus 1. Okay, sorry about that. I had a little bit of a computer glitch. So we're right here, and we've got our u equals 1 over x. So that's x to the minus 1. So how do I take the derivative of x to the minus 1? Well, it's minus 1 x to the minus 2 dx. All right, now just looking at it, that might not look like what I've got, but if I make a little bit of an algebra swap here, then that starts to look a lot more like what I've got left. All right, so the only adjustment I'm going to have to make is for this negative sign here, which I'll simply bring that over to the other side. All right, so now my u is up here, right? That's my u. And then my du is kind of like this. It's right there. All right, so I've got the negative sign, which is just a negative 1, so I'm just going to bring that outside. E to the u du. All right, and what's the antiderivative of e to the u? Well, that's the easy one. Remember, that's just e to the u plus c. All right, so we get negative e to the 1 over x plus c, like that. All right, now I have one other to show you here, and that is this one. All right, now logarithms are a little different. And one of the reasons logarithms are a little different is we don't have a way to take the antiderivative of a log. So, if you have an integration problem that has a log in it, then that log has to be your u. You don't have a choice. You cannot antidifferentiate ln of x, not yet anyway. And because we can't antidifferentiate ln of x, we can only differentiate it. Then there's no thought involved here. If I see a natural log in the problem, the natural log should be my u. Alright, whatever it is. I realize that's a composite function. That's okay. Alright, but that has to be my u. So I just have to work with it. So then du, how do we take the derivative of the natural log? Well, it's the inside. I'm sorry, it's the derivative of the inside over the inside dx. Alright, so this just becomes 1 over x dx. And this is pretty straightforward now. Alright, that's my du. Don't have to do anything with constants because they canceled out. Alright, so I just have the antiderivative of, well, ln of 5x is my u. 1 over x dx, which is what this is my du. Alright, so this is about as straightforward as it gets. 1/2 u squared plus c. So this is 1/2 ln of 5x squared plus c. Just like that. Alright, so you've got a few examples here that you can go back through. Alright, got one that involves a nice e there. Alright, a couple of rational expressions. A couple of basic ones. Alright, and just remember, composite functions require a u substitution.